How does an electric car run smoothly without a drop of gasoline? Beneath its sleek exterior lies advanced technology. Batteries, motors, and controllers working together seamlessly to transform stored electricity into silent, efficient motion. It's innovation in action. The story begins with the heart of every electric vehicle, the battery pack. Think of this as the fuel tank, except instead of gasoline, it stores electricity. But it's not just one battery. It's a meticulously designed system made up of hundreds, sometimes thousands of smaller lithium-ion cells. Each cell is a small cylinder or pouch that works together to provide the power needed to drive the car. When combined into a pack, these cells can store an impressive amount of energy. For instance, a Tesla Model S has a battery pack capable of holding up to 100 kilowatt-hours, enough to drive over 300 miles on a single charge. Why lithium-ion? These batteries are incredibly energy-dense, meaning they can store a lot of power in a relatively small space. They're also rechargeable, making them perfect for EVs, which rely on frequent recharging to remain practical. But these batteries don't just sit there, they're constantly monitored by a battery management system, or BMS. In addition to ensuring safety and longevity, the battery management system also plays a critical role in the performance of an electric car. It monitors factors like voltage, current, and temperature to maintain optimal conditions for the battery cells. For example, if the temperature rises too high during charging or driving, the BMS will activate cooling systems to prevent overheating. Advanced BMS technology can even predict potential issues before they occur, ensuring reliability and minimizing downtime. As EV technology continues to evolve, the integration of artificial intelligence into BMS systems promises even smarter, more efficient energy management. The importance of software in EVs extends beyond battery management. Modern electric cars are equipped with sophisticated systems that continuously monitor and optimize performance in real time. From navigation systems that suggest the most energy-efficient routes to adaptive cruise control that maximizes range, software plays a critical role in ensuring a smooth and efficient driving experience. Over-the-air updates, a feature popularized by Tesla, allow automakers to improve the car's performance, add new features, or fix potential issues remotely, ensuring the vehicle remains up to date without ever needing to visit a service center. This combination of hardware and software makes electric vehicles not only mechanically superior, but also smarter and more adaptable than traditional cars. The BMS ensures the cells are charged and discharged evenly, prevents overheating, and optimizes the battery's overall performance and lifespan. Without the system, the battery pack could degrade quickly or even fail entirely. So how does this stored energy translate into movement? This is where the electric motor comes in. If the battery is the heart of an EV, the motor is its muscles. Unlike an internal combustion engine or ICE, which burns fuels to create energy, an electric motor uses electromagnetic principles to produce motion. Here's how it works. When electricity from the battery flows into the motor, it generates a magnetic field. This field interacts with permanent magnets or electromagnets inside the motor, creating a force that spins the rotor, the moving part of the motor. This spinning motion is what ultimately drives the car's wheels. Electric motors are incredibly efficient. While traditional gasoline engines waste a significant portion of their energy as heat, electric motors convert over 90% of the electricity they receive into motion. This efficiency is one of the reasons EVs are much more economical to operate than gasoline-powered cars. And there's another benefit: torque. Unlike an ICE, which needs to build up power gradually, an electric motor delivers maximum torque instantly. That's why EVs are known for their incredible acceleration. Press the pedal and the car surges forward without delay. But there's more to an electric vehicle than just its battery and motor. Another critical component is the controller, often referred to as the brain of the EV. The controller manages the flow of electricity from the battery to the motor. It takes input from the accelerator pedal and determines how much power to send to the motor based on how hard you press down. The controller also plays a crucial role in ensuring the motor operates smoothly and efficiently, making it a key player in the seamless driving experience electric cars are known for. Let's talk about one of the most fascinating features of EVs, regenerative braking. If you've ever wondered what happens when you hit the brakes in an electric car, the answer is both clever and efficient. Instead of wasting energy as heat like traditional braking systems, regenerative braking converts the car's kinetic energy back into electrical energy. This is achieved by running the electric motor in reverse, turning it into a generator that sends power back to the battery. It's like recharging energy every time you slow down, which not only extends the car's range, but also reduces wear and tear on the traditional brake system. Charging an EV is another area where technology has advanced significantly. Think of it as similar to charging your phone. You plug it in, wait for it to recharge, and then you're ready to go. But unlike phones, electric vehicles have multiple charging options. Level 1 chargers use standard household outlets and are the slowest, adding just a few miles of range per hour. Level 2 chargers, which are commonly installed at homes and public charging stations, are faster, providing up to 40 miles of range per hour. Then there's Level 3 or DC fast charging, which can charge a battery up to 80% in as little as 30 minutes. Governments and private companies are heavily investing in these networks, ensuring the infrastructure grows alongside the demand for electric vehicles. If the electricity comes from renewable sources like solar, wind, or hydropower, EVs are incredibly clean. However, if the grid relies heavily on fossil fuels, the benefits are less pronounced. One of the most significant advantages of electric cars over traditional vehicles is their mechanical simplicity. A gasoline car has hundreds of moving parts in its engine alone, including pistons, valves, and crankshafts, all of which require regular maintenance. An electric car, by contrast, has fewer moving components. The electric motor, for example, has just one moving part, the rotor. This simplicity translates into fewer breakdowns, lower maintenance costs, and a more reliable driving experience. The environmental benefits of EVs are another major selling point. With zero pipeline emissions, electric cars are helping to combat air pollution and climate change. But what about the future of electric cars? The possibilities are truly exciting. Self-driving electric vehicles could transform transportation, reducing accidents and making commutes more efficient. Wireless charging, where cars can recharge simply by parking over a special pad, is already being tested. And then there's vehicle-to-grid technology, which allows EVs to feed electricity back into the grid when they're not in use. This could help stabilize the grid during peak demand and even provide backup power to homes during outages. As the video draws to a close, it's clear that electric cars are more than just a new type of vehicle. They're a symbol of progress. They represent the future of transportation, combining innovation with sustainability to create a cleaner, quieter, and more efficient way to travel. So, what do you think? Are you ready to make the switch to electric? If you enjoyed this deep dive into how electric cars work, make sure to give this video a like, share it with someone curious about EVs, and subscribe to our channel for more insights into the world of technology and innovation. Thanks for watching, and see you in the next video.